this is Mark, and this will be my homework 10, and this will be the last video for this quarter. Before that, I'll show you my room around, and here's my problem statement with the formula sheet and constant sheet. So, let's get started. That's the last time I'm going to say this for this whole quarter. We know, for this one, it's pretty complicated, but we need to draw a graph first and analyze a three-body diagram. Well, for the sake of simplicity, I'm not going to draw like a full graph. I'm just going to draw the part indicating the tube, so it's easier to understand. So for the first graph, we know that in each individual section, WAL. So for the first part, we'll call this the left side and this the right side. Focusing on a three-body diagram, we see at this place on the piston, there's three forces: mg PA times AL, which is the area of this; PW, which is the pressure of the water, times AL. PAL is the left side of the air pressure, by the way. To fully utilize this, we need to first analyze the laminar flow of air. So we know we can use the Bernoulli equation for it. Left side has such that PAL plus, they are the same height, so they have the same potential energy, skipping that part directly. PAL plus half of rho air VL squared equals to PAR plus half the air VR squared. This will give us that the pressure on the left side is actually smaller than the pressure on the right side because there's faster flow. How do we know this? Because it says the diameter is 2 times as large. We know by continuity equation that AL of the tube VL equals to AR VR. Remember, this is A prime R, so it's a different thing. The surface area of the cross section on the right side is 4 times as big as the left side because it has 2 times diameter. Thus, we will be able to get that the velocity on the left side is 4 times of its velocity on the right side. And the higher velocity there is, the lower pressure it has on the region. By this logic, we can simply say that PAR minus PAL equals to meters squared, VR equals to 4 meters squared. On the left side, we will get this AL minus AR minus AL is half of rho air VL squared minus VR squared. Here is some of the analysis. Now we are able to find the actual velocity of the right side, which is a quarter of 30, which is 7.5, but I'm going to write it as that. And here is the equation we're going to use a bit later. How do we use it? Well, simple. We know that at a point it's a static object for both pistons, so it must satisfy the equation that on the left, PW, which is the pressure of water, times AL, which is the cross-sectional area, equals to PAL times PL minus a mlg. mlg is the mass of the piston on the left side. We don't know the exact number, but doesn't matter because these two will later be used as equivalent substitution. You will see what I mean later real quick. So PW equals to PAL minus MLG divided by AL. Same logic for right side. We can just quickly simplify it. Equals PAR minus MRG AR. Putting these together, we will get PAL plus PL plus MLG AL equals to PAR plus MLG AR. What would this become? This would become PAR minus PAL equals to MLG AL minus MRG AR. That's the other equation we will find. Here, voila. We have found this equation, and it will come later at a very important moment to clutch the solution. Well, we have found everything we could find in the first case. Now let's move to the second case, where the pistons on the left side move down and the right side moves up. Why is that the case, you say? Because currently the left side has less pressure exerted on the right side has more pressure. When both of the pressure increase, but the left increase by more, so it pushes the left harder than it pushes the right, and it bumps up with a separation of height difference. Let's call this height difference delta H, right? So now we still can find PW. How? We know that PW prime L equals to PW prime R minus rho water times G times delta H minus difference. This is Pascal law, right? It's an important equation. Here we have this. Why is that case? Because after the top laminar flow stops, it moving to a new equilibrium. So we can use the rule we just used basically again. It states such that, I'll just write everything because repeating every single word here is frankly quite hard. G divided by AL, PWR, PA, plus MRG, AR. Such that we get PA prime plus MLG AL equals to PA prime plus MRG AR plus rho water G delta H. Voila. Here's the calculation we're gonna get using this new position in mind. These are essentially the same equation derivation from the top, but now it's in, you can see the prime side because it's in a new situation. These two are the same now because it's a static liquid. Well, static fluid, not liquid, but it's moving at 30 meters per second before. It was treated as incompressible. We can see clearly on the left side, after the whole conversion, we could put this side onto this and follow this identity upward to calculate the eventual delta H. These two PA prime cancels out, which gives us a convenient answer. Going deeper into the solving process, we will know that MLG minus AL MLG AR equals to G delta H. Then we will get this equation by a bit of simple shifting from here, just equating this up to here and this back to here. We'll put this over to here. Now we're left with all of the known variable, and we can simply calculate our delta H, which is the height difference we're looking for. So let's punch everything into the calculator for one last time. Using the density sheet, we can find the density of air as 1.2 and 30 squared minus 34 squared divided by 1,000 1 equals to, here we have it, final answer. And that is in meters, so a bit of unit conversion later, we will have 5.16 centimeter. And that is height difference. That's how much higher the right side is compared to the left side after we turn the wind off. One last time, I will show you the entire graph, how I derived it, and every equation I've used. Sorry. Here's the final. Alright, that'll be it. Thank you all for grading my homework and teaching us. Bye.